Hi everyone, and welcome back to the drug checking webinar series from the BC Centre on Substance Use. In this video, I'm going to introduce the software that is used for drug checking and the basics behind analyzing drug samples on the FTIR. We recommend that if you have not watched the introductory FTIR webinar, that you watch that one first. In this webinar, we're going to introduce you to the fundamental mechanics and flow of a drug check. By the end of this webinar, you should be able to describe the basic flow of analyzing a drug sample in OPUS, demonstrate the ability to navigate the OPUS software and identify the relevant functions used for drug checking, translate the format the results come in to be able to communicate these to service users, and finally, name the libraries that we use for drug checking and be able to identify why and when to use each one. All of the steps that I will outline in this video are written in the Operational Technician Manual. It will be your go-to resource for all things spectrometer and OPUS related. To download the manual, visit our website at drugcheckingbc.ca. Let's start by going over the OPUS software and the basic parts of the main window. OPUS is a proprietary software of Bruker that allows us to measure and examine infrared spectra that are collected with the FTIR spectrometer. It is the software we use to analyze samples submitted to drug checking. We are going to go over the Drug ID Wizard version of OPUS in these webinars, as that is what we use for drug checking in British Columbia. If you are using the regular, full OPUS software, the look may be slightly different, but the general functions are the same. I should also note that the layout of the screen is customizable and may differ computer to computer, so it's important to know the functions and where to find them. What you'll see during this webinar is my preferred layout. As you may recall from the introductory FTIR webinar, FTIR spectroscopy measures samples to produce what we call spectra, which are graphical representations of the sample's chemical composition. The center of the screen is where the spectra are displayed. This is called the window. In this spectrum window, you can manipulate the spectrum by stretching it up and down, zooming into particular areas, or checking the wave number of particular peaks. Along the bottom, the x-axis scale of the spectrum is the wave number. These values are important as it's a representation of the frequency of infrared light that is either absorbed, causing a peak, or not absorbed, causing a flat line. The left side of the screen shows the large buttons that progress you through a drug check from measuring a background, to measuring a sample, to moving on to the next sample. We're going to expand more on what each of these steps looks like later in the webinar. At the top left of the screen is the OPUS browser, which may or may not be collapsed and hiding. This little window shows you how many files are loaded into the software and how many windows are open during the analysis. I like to keep track of our task function buttons on the right side of the window. These buttons are shortcuts for steps in the analysis of any sample. The magnifying glass is called Spectrum Search and opens a window to perform analyses. We'll talk in great detail about this button in a few minutes. The other shortcut buttons here are the Load and Unload files, which allows you to bring in an older measurement for further analysis or to eject the current one when you are ready to move on. At the very top in the taskbar, there are more functions in the drop-down menus. At the very bottom is where you will find the green bar that indicates that a process is running. We went over this in the last webinar, but I'll briefly mention that when a process is running, that is, the bar is green, it's best to leave OPUS alone and let it finish its task. It can become overloaded with operations and is prone to crashing, so just let it be when it's working. When the bar is blue and says no active task, it is done running the process and is good to go. For this webinar, I'm going to assume the sample has been properly measured according to the procedure I laid out in the last video. If you are following along, load a spectrum file in by pressing the Load File button and selecting a file. Each analysis can be broken down into a two-step process at its most basic level. The first is called a subtractive analysis. During this step, we progressively subtract reference compounds from our measured spectrum, sequentially identifying ingredients in the sample. The The second is called mixture analysis. This step uses an algorithm in the OPUS software to assign percentages to each ingredient, providing approximate proportions on ingredients. We start on every sample with the subtractions. Pretty much all analyses you're going to perform on a spectrum can be accessed through this button, the spectrum search. Clicking on it will open a window with 3 tabs. I'm going to go through them now. The first tab is called Spectrum Search. In this tab, you can select which sections of the spectrum to use for the search you're about to perform. To start, ensure that Use File Limits is selected. This setting uses the entire measured spectrum and searches it in its entirety against the reference libraries. The second tab is Search Parameters. In this tab, you select which analysis type and algorithms to use. For the subtractive analysis like we're going to do now, use spectrum correlation with vector normalization and first derivative. In basic drug checking, there is no other type of normalization to use here, so always stick to first derivative for the best results. Briefly, vector normalization removes the intensity differences between the measured and library spectra, and first derivative is just like it sounds, assessing the slope of the line to see the correlation between the measured and library spectra. For a much more in-depth explanation, check Chapter 9 of the OPUS manual available from Bruker. The third tab is called Select Libraries. In this tab, you select which reference libraries you want to search your spectrum against. Let's walk through the available libraries. There are several libraries available for drug checking, but depending on many factors, some might not be available at all times. One FTIR library that you will always have access to is called SWIG-Drug, which stands for the Scientific Working Group on the Analysis of Seized Drugs. This is a free FTIR library that is put together by this working group, whose members are representatives from police drug labs across the world. It is available for download from swigdrug.org and is generally updated once or twice a year. Another common library is called TICTAC, made by an organization based out of London, England. This library is not free, however, and it requires yearly licensing, which can be quite expensive. It's updated about once a year. The third library we use is called the BCCSU FTIR ATR Library of Drugs and Common Adulterants. This open source and free library contains lab-confirmed drug samples brought in for drug checking in British Columbia. It also contains some of the most common adulterating agents. The reason we created this library is because there are some new psychoactive substances that appear in our drug checking service that do not have available references yet. This is because other libraries are updated irregularly and infrequently. When a sample comes in for drug checking that does not have a reference, we can forward the sample for confirmatory testing in the lab, and once it's confirmed, we can use the original FTIR scan as a reference for future samples. These 3 libraries are what we call the primary libraries, and are generally the 3 that you should have on when drug checking. There are, however, other libraries available. These other libraries are much larger and contain obscure compounds that don't come up very often. The reason we generally don't have them on in the primary analysis is because they are so large, containing thousands of compounds, it makes subtractions very slow to perform and increases the time it takes to complete a drug check. The Bruker Pharma library is the largest, containing almost 10,000 compounds. The majority are chemicals that are not relevant to drug checking. The other is the Georgia State Crime Lab Library, which has over 2,000 compounds. These libraries have some things that come up while drug checking that are not contained in the primary libraries, but it's still preferred to keep them off generally. Knowing when to turn them on because there is signal in the sample from something that is not contained within the primary libraries is one of the skills you will learn to develop. Okay, back to our sample, let's select the 3 primary libraries and click Search Library. The results of the spectrum search are displayed by descending hit quality. Hit quality is a score out of 1,000 that ranks how well the searched spectrum correlates to the library entry. High scores are better, but the number itself does not mean too much. By default, the red spectrum is our spectrum, the one we measured and are working with. As we progressively subtract components, it will look different as signal is removed, but it will always remain red. The other colors are just to distinguish them from our spectrum being measured. You can see in this case the first match is cocaine hydrochloride, or powder cocaine. The reason it's showing 3 times is because cocaine hydrochloride is in all 3 of the libraries we have turned on: SwigDrug, TicTac, and the BCCSU library. All 3 entries are effectively exactly the same because they are all just cocaine, but minute differences may cause subtractions to return different results. What we want to do now, though, is evaluate how well the cocaine references match our sample. In the window, right-click and select Shift Curve, then Top. This allows us to drag the peaks up and down to evaluate how well the spectra match. Here, I'm dragging up the peaks to match. Look at the area highlighted on the screen, and you can see how the 2 spectra match in this region. This means that cocaine is likely in this sample, but we need to evaluate more areas of the spectrum before we can call a conclusive match. The highlighted region of these bifurcated peaks is very characteristic of cocaine and easily recognizable when you start to recognize the patterns. For more examples of these characteristic peak signatures, check out our resource, FTIR Signals of Common Compounds. These reference sheets exist for some of the most common things you will come across and describe not only what they are, but how to recognize them in samples. With time and enough practice, though, it will become second nature to recognize these patterns, but starting off, this can be a very helpful resource. Continuing with this sample, let's confirm that there is cocaine by checking another area. Looking over here, you can see that signal in our red spectrum is accounted for by the reference entry for cocaine. However, there are peaks or signal in our red spectrum that are not present in the reference. What this means is there is something else present in our sample that is not accounted for by cocaine, indicating a second or possibly third component. To find out what this is, we want to remove the cocaine signal to evaluate the next match. To do this, right-click on the library entry and click Auto Subtract a New Search. This function removes the cocaine signal from our spectrum, and on the residual or remaining signal runs a spectrum search using the same parameters we locked in earlier. Now that the cocaine signal is subtracted out of the spectrum, the remaining signal is matching to something called phenacetin. Right off the bat, I know that this is a very plausible match because phenacetin is a common cut in cocaine. That's not enough to go off though, we still need to evaluate how well the phenacetin reference matches our residual spectrum. To do that and match up the spectra, again, I'm right-clicking, then Shift Curve, then Top. You can see from the highlighted sections on the screen that there are parts of the spectrum that match very well. It's not going to be a perfect match though, because we have already subtracted the cocaine signal out, so when that happens, we lose signal from the phenacetin where the 2 spectra interfered. If 2 compounds both have peaks at the same wave number, the spectrometer cannot tell which compound is responsible for that absorption, so we lose the signal if we subtract it out. This phenacetin looks like a good match, so again, I'm going to right-click on the library entry and auto-subtract a new search. The resulting line is pretty flat. It's flat because there is no signal remaining. No signal means there are no other compounds present that are not accounted for by our 2 ingredients, cocaine and phenacetin. One of the hardest parts about doing analysis like this is knowing when to stop by being able to tell when there is no signal remaining by evaluating the line. In this case, there are no clear peaks in the signal. It's relatively flat, and any ups and downs are due to noise in the signal and not a third component. As you gain more experience with drug checking, you'll get more confident in deciding when to stop looking. But if you're ever unsure, you can always ask another technician for a second opinion. Now for the second step in a drug check, which is called mixture analysis. Briefly, mixture analysis is a function in the OPUS software that uses an algorithm to break down the measured spectrum and tries to recreate it with library entries, thereby estimating the proportion of compounds. The result is called a composite spectrum and is displayed with a percentage makeup of signal. I'll show you how to perform a mixture analysis now. Before we go into the menu to perform a mixture analysis, it's important that we are running the analysis on the original spectrum that has not had components already subtracted, or else you will run a mixture analysis with components already missing. Using the window navigation at the very bottom of the window, return to an earlier one where the original spectrum is displayed. When a window is open, you can also click the X on the right-hand side to close it. Now, using the same spectrum search button on the right-hand side, click on it once again to open the pop-up window. Using the middle tab, Search Parameters, select Mixture Analysis on the right-hand side. At this point, we have some decisions to make. Because Mixture Analysis uses library entries to recreate your spectrum, we need to tell the algorithm the maximum number of entries we are allowing it to return. Thinking back to our subtractions performed a few minutes ago, we know that there are two components present, cocaine and phenacetin. So for this mixture analysis, I'm going to select two components. In the third tab, Select Libraries, we have the ability to control what libraries are used in the mixture analysis. Remember how libraries have overlapping entries and things like cocaine are in each of the libraries? By restricting the libraries at this stage, we can control the output of the mixture analysis to prevent duplicates, which often happen if there are components present in small amounts. For this particular sample, I'm going to use only one library, the BCCSU library, because I know for a fact that both cocaine and phenacetin are present as entries in it. Also, the more libraries turned on for mixture analysis means it runs a lot slower. By using only the BCCSU library, our results are returned a lot faster. I'm ready to run the analysis, so I'm going to click Search Library. Here are the results from the mixture analysis we just performed. In the window, you can see three different colored lines. As per usual, the red line is our spectrum we are analyzing. The purple line is called the composite spectrum, which is the algorithm's attempt to recreate our red spectrum using library entries. You can see that in this particular analysis, the composite spectrum was determined to be 93.8% cocaine and 6.2% phenacetin. The green line is called the residual, and this is the difference between the red and purple lines. So how do we interpret this information? Well, from this particular mixture analysis, you can see that the composite, which is the purple line, and our spectrum, the red line, are very similar. This is also indicated by the green line being pretty flat, showing us that there is very little difference between the two spectra. This means that the composite spectrum is a good recreation of our spectrum, and therefore the mixture analysis was a success and pretty accurate. It's important to note here that these percentages refer to the proportion of signal in the spectrum. But according to physics, and specifically the Beer-Lambert law, we can make the assumption that these percentages are representative of the sample because light absorption is directly related to the chemical makeup of the sample. Mixture analysis can be a very powerful tool when used properly. However, there are a lot of drawbacks and things to know about. During your shadowing experience, you will come to know these with more detail, but I'll go over the main ones now. Mixture analysis will often not return components when they are present in the sample below 10% because the algorithm will fail to recognize them. Components like fentanyl will often be detectable during subtractions, but mixture analysis will not detect it at this stage and therefore will not assign it a percentage. That doesn't mean it's not there, it's just a major limitation of the mixture analysis algorithm. Second, similarly, mixture analysis will often return false results that were not detected during the subtractions. As it's just trying to recreate the measured spectrum, it can return false results. The golden rule of mixture analysis is to never immediately believe a result reported by it that wasn't first detected during the subtractions. If something is reported that you did not see during the subtractions, you can definitely go back and reevaluate, but just don't believe it right away. Mixture analysis is only for aiding in the estimation of proportion or percentage, not for identifying additional components. Finally, using different search parameters will affect the outcome of the analysis. Results are affected by which libraries you have turned on and how many results you tell it to return. This means that sometimes more than one mixture analysis will have to be performed to narrow in on the results. Knowing how to do this will come with experience, but it takes some trial and error. To recap, there are 2 steps in OPUS for the basic analysis of samples for drug checking. Subtractions, followed by mixture analysis. Of course, this would be followed by or done concurrently with fentanyl and possibly benzodiazepine test strips, depending on the sample. Once the results from each test type are ready, the next step is for you as the technician to think through the results and come to a conclusion about the sample. When that's done, you can relay your conclusions to the person who owns the sample, along with the corresponding harm reduction advice or relevant information. Communicating results with people accessing the service is a skill that comes with lots and lots of practice and frontline shadowing experience. We will have a webinar and some corresponding training resources to assist with this, but the best thing you can do to learn how to communicate results to service users is to shadow other technicians. That's it for this webinar introducing the basics of the OPUS software. The other finer details will come up in your shadowing and actual drug checking experience. In this webinar, you learned how to 1. Describe the basic flow of analyzing a drug sample in OPUS. 2. Demonstrate the ability to navigate the OPUS software and identify relevant functions used for drug checking. 3. Translate the format the results come in to be able to communicate those to service users. And 4. Name the libraries that we use for drug checking and be able to identify why and when to use each one. Thanks for watching. For materials related to these webinars or to access drug checking results from across the province, visit our website at drugcheckingbc.ca.